Find a vector line integral of a given vector field along a closed curve C encompassing the origin. First of all, we can calculate partial q partial x and partial p partial y to see that they're equal, which gives us the impression that we may want to use either the fundamental theorem or the Green's theorem. But at a closer look at the expression, we can see that neither of these two functions are defined at the origin, which means that the domain of the vector field actually does not contain the origin, and therefore it's going to have a hole. So on a graph, it's going to look like this. We're going to have the domain to be all the points on the xy plane except the origin, which is a hole. And because of this hole, the region that we are going to be working on is not going to be simply connected. And therefore, the vector field must be non-conservative. And because it's not conservative, fundamental theorem does not apply. Okay, so that leaves us with the next option, that's to use the Green's theorem. If we want to use the Green's theorem, then we will need to turn the line integral into double integral over the region enclosed by the curve C. So we will be working on the partial derivatives. Okay, so in the pictures, it's going to be look like this. The curve C is going to be going counterclockwise direction, and then it's going to enclose the origin. So we now see another problem. That is, this point, the origin, is still contained in the region bounded by C. And neither these two partial derivative is defined at the origin. Okay, so that means we cannot apply the Green's theorem directly for the region like this. So what do we do? If we think about it, we see that the problem here is exactly this point, origin, which we call it a singular point, because it is this point that makes both these two functions not defined and these two functions not defined. In order for us to use the Green's theorem, we must try to think of a way to remove this point from the region to kind of take it out. Okay, so the idea here is that we're gonna try to construct a simple curve to go around the origin. So sort of cut it out so that we can have a new region for us to use the Green's theorem, and then over the new region, we can guarantee that both these partial derivatives are defined. Okay, so let's think about how we can create this simple curve. For example, I can just choose anything like a rectangle or like a triangle to enclose this. Okay, anything that is simple, that will work. But one of the most convenient way to do it is that we just use a circle, and then we're gonna denote this circle by C1, because the requirement of the Green's theorem, we will need that this circle to be oriented clockwise. So it's going to be going in this direction. Okay, so let's try to write out this line integral in the expression of C and C1, and we will see how it goes. We're going to write it as line integral of C and C1, and then we're going to counter this by using a reverse C1, F dr. And then by the distributive property, we can write this as integral of C and C1 of F dr, and then another line integral of the reverse C1 of the same thing. Okay? And then we will take a look at what this C and C1 gives us. C and C1 is going to give us a new region, which is highlighted by this blue marker, because obviously C and C1 is going to be the boundary of this new region. Okay, so by the Green's theorem, we can turn this part into the region, double integral of the region D, where D denotes exactly this region, of the expression partial Q partial x minus partial P partial y dA. Okay, and then for this part here, it's just gonna be simple evaluation of like a single variable definite integral. So that's gonna be we're gonna be substituting a parametric equation into this function, where the parametric equation represents the reverse C1, and that is gonna be what is that called? This is gonna be from dr. Okay, so that's gonna be from alpha to beta. Sorry, r prime t dt. Okay, so it's gonna be like this. Okay, so let's work on these calculations. For this part here, we see partial q partial x and partial p partial y. They're both defined on the new region, because the new region does not contain the origin. So there's no problem of calculating this part. And we also see that partial q partial x equals exactly partial partial p partial y. So this minus that is gonna take us to 0, because these two are canceled. Okay, so this part is gonna be 0, and then let's work on this part. For this part, we're gonna take a look at the parametric equation of the reverse C1, which is gonna go counterclockwise, okay, counterclockwise direction. And because this is a circle, so we can just write it as r of t equals a cos of t and a sine of t, where the constant a represents the radius of this circle, and we can choose the constant a to be small enough such that the entire circle is contained in this outer curve. And because it's going counterclockwise, we can have t to be ranging from 0 to 2 pi. For convenience, we also calculate r prime of t, which is negative a sine of t, and then a cos of t. Okay, and then this one is going to be turned into from 0 to 2 pi. This guy is going to be, what is that? We're going to replace x variable with this a cos t, y variable with this a sine of t, okay? And then x squared plus y squared is going to be radius squared, which is going to be a squared. So that's going to be y is going to be a sine of t, and then divided by a squared. And this x is going to be cos of t, and then divided by a squared. And this going to dot product with r prime. R prime is this guy, which is negative a sine and then a cos t dt. Okay, dt, then we do the dot product. It's gonna take us to from 0 to 2 pi, and then all the a's will be cancelled. So that's negative sine squared t plus cos squared t dt. Because the sum of the squares equals 1, so that's negative 1 dt, which is negative 2 pi. Okay. So now we have finished evaluating the given line integral by using the Green's theorem indirectly.